So yeah, thank you, Miguel, for invitation and introduction. So yes, today I'm going to talk about the recent paper that I put out like last December, together with Yu Yakusuki in the Kyushu University, Marco Maineri in Torino, and Hiroshi in the audience about the continuous family of conformal field series, well, more specifically conformal manifold, and its relation to exactly marginal operator. So let me start. By the way, if you have any questions, feel free to interrupt at any moment. So, so of course, for this seminar series, I guess I don't need to introduce swampland program, but let me just say that well, uh, the swampland program is a kind of idea that the quantum gravity has non-trivial inference on the IR effective field theory, like a low energy effective field theory. And the slogan is that in quantum gravity, not every low energy effective field theory is allowed. And And also, I don't need to introduce these examples, but the two famous example, which are actually maybe these two are kind of the most or are on the most solid ground. Are The first one is a no-free parameter conjecture, which basically says that all parameters in quantum gravity. So, let's take some effective low energy effective field theory, which come from the UV consistent quantum gravity. And if you just look at effective field theory, then it might look like that field theory has some free parameters that you can change, like a mass of the particles or the coupling, the strength of the coupling constant. But in the UV complete quantum gravity, the conjecture says it must come from the vacuum expectation value of basically some moduli fields. And the simplest example is that in the string theory, the string coupling constant is coming from the expectation value of the dilaton. And another one is what's called no global symmetry conjecture, and which basically says that in UV complete quantum gravity, there shouldn't be any global symmetry, and then global symmetry in the IR should be either gauged or broken in the UV complete quantum gravity. And people often also talk about these two on the same footing. And then there is a sense in which the first conjecture, you can think of it as a kind of absence of minus one form symmetry conjecture. Okay, so these are two famous examples. And obviously, it's a very interesting conjecture, and they are very, very interesting conjectures. And if they are true, they will provide non-trivial constraints on the space of allowed gravitational effective field theories. And as many of you know very well, better than me, there are many indirect arguments and evidence, but of course, these are still conjectures, and it is at the moment difficult to provide a proof or a more rigorous argument. And so one big question is whether we can provide a more rigorous or a proof or non-perturbative proof of these conjectures. And today I'm going to talk about the first one, focus on the first one, which is the no-free parameter conjecture. So now, what would be the strategy for getting some kind of a proof or a rigorous argument, which basically justify these conjectures? Then, if you think about it, let me just highlight this part of this sentence. So these conjectures, as I said, if they are true, they will provide a non-trivial constraints on the space of gravitational EFT. And if you think about it, there are actually methods people are using in slightly different field, but of course, in the context of QFT in string theory, which will actually allow you to get some non-trivial constraints in a rigorous way about the space of effective field theory. And that's, as many of you are already aware, I guess, are conformal or S-matrix bootstrap, which are topics actively studied in the past 10 years. And the basic idea of the conformal bootstrap are to kind of get some non-trivial constraint, and in particular, oftentimes they are rigorous, about the low energy data from very basic principle like unitarity or associativity of operator product expansion or analyticity in the kinematic space of the S matrix. And so those are developed mostly for non-gravitational theories. Many of great applications you heard about are mostly for non-gravitational theories. And in particular, of course, like a conformal bootstrap is precisely about the non-gravitational theories, which are conformal field theories. And there are like a recent works about like a S-matrix bootstrap for gravitational theories. But of course, like there are like I think there are more results for non-gravitational theories. So I would say like it's mostly studied for non-gravitational theories so far. And so in that sense, like you might think that this does not give a direct implication for like a swampland conjecture for which gravity is important. But of course, the advantage of this bootstrap method is that it often provides a rigorous predictions on the space of consistent theories. So the bounds that you get from the bootstrap are rigorous. And so the natural question is, can we use the power of the bootstrap to say something rigorous about swampland conjectures? And uh, and the point of the talk is that it is possible if you use the ADS-CFT correspondence, because the ADS-CFT correspondence allows you to translate swampland conjecture in quantum gravity, in particular in ADS, asymptotical ADS spacetime, to conjectures in conformal field theory. So now, like after the translation, they are just conjectures in conformal field theory, and you can prove it by CFT arguments. Well, if you are lucky. So that's the basic philosophy that I'm going to follow in this talk.
So, Shota,
And yes,
can I quickly ask, the arguments you're going to present, is there any sort of decompactification or flat space limit that you can take to pull back the conclusions to flat space in any way?
that's uh, that's a very good question. Yeah, actually, well, of course, like there is a like a one needs to show that the flat space limit is smooth, and then there is nothing like a phase transition happening. But uh, there is no obvious like a difficult like a possible phase transition that I can immediately point to. So it could be that like with a little bit more arguments, you can actually also try to take the flat space limit. But of course, like existence of the flat space limit itself is a non-trivial like a non-trivial thing to prove, especially from the CFT point of view. Okay, so so this is the plan. So let me first, like in the first part, I'm just going to translate the no-free parameter conjecture to the CFT statement, and I'm going to provide a proof in 2 dimensions. And I'm going to give you a little bit of technical details because it's a kind of simple algebraic manipulations, and I suspect like this kind of algebraic manipulation might be useful for other purposes. And then I will end with some comments and conclusion. Okay. All right. So let's start from translating the conjecture to the CFT statement. So let me recap. So the conjecture that I'm talking about is this no-free parameter conjecture, which basically says that all parameters in quantum gravity in ADS spacetime needs to be a vacuum expectation value of some fields, like a moduli fields. And so so this basically, so in order to translate this statement, we first need to think about some like quantum gravity theory in ADS with some parameters. And of course, like if you believe in ADS CFT dictionary, then if you have some parameters in CFT, sorry, in quantum gravity in ADS, that immediately translate to some one parameter family of conformal field theory. And so that's a kind of basically translation of the left-hand side. And so then the question is, what is the translation of the right-hand side? So the translation of the right-hand side is also simple. So let's imagine you have some like a field theory in ADS, and some field gets a vacuum expectation value. And so in particular, that particular field should have also like a non-zero expectation value at the boundary of ADS spacetime. And if you remember like a usual GKP Witten dictionary, these like asymptotic behavior of the fields in ADS, and in particular the constant part of the massless modes in ADS spacetime corresponds to basically coupling constant for marginal operators. And the reason why it is marginal is because if you have some moduli fields in ADS, then because by definition, I'm assuming the moduli to be flat, So it should correspond to some massless fields in ADS. And if you use the usual dictionary, which relates the mass of ADS to the dimension of the operator, you can see that like this dimension, that operator dual to this field must have dimension D, which is marginal operator. And furthermore, like this field is massless, like at any point on the moduli space. That means that the corresponding operator should be exactly marginal. Okay, so it's marginal at any point of the CFT moduli space. And so therefore, so you can easily translate both sides of this equation into the following CFT counterpart of the no-free parameter conjecture. So the CFT counterpart of the no-free parameter conjecture says that if you have a continuous family of conformal field theory, they must be generated by exactly marginal operators. And we can also phrase it in a more kind of like a standard CFT language. So the continuous family of CFT basically normally people call it like a conformal manifold. There is a continuous family of CFT which are related, which are connected continuously with each other. And what this means, what this sentence means, which is like must be generated by exactly marginal operator, means that you can move around different points on the conformal manifold by basically exponentiating this particular exactly marginal operator. So
So
Shota,
I
can
have a
I ask a
question.
question? Oh, sorry.
yes, there are several people. Yeah,
Hassan, you
maybe.
want to go first or?
Okay, thank you. So I just wanted to ask that, are you
Mhm.
making this conjecture for all CFTs or just holographic CFTs?
So here, yes, so this conjecture itself, we are going to talk about it in all CFT.
Okay,
But
so
in
whether
order
or not
to
they're
translate,
holographic.
yes, in order to translate the statement to the CFT, we basically first translated the statement in the holographic regime because otherwise I cannot make a direct contact between quantum gravity and CFT. But once you translate the conjecture to CFT, uh, you can try to prove it for all CFT. And then the claim is that this seems to be true under certain assumptions.
Okay, I see. Thank you.
Uh, Thanks. Yeah, the question I have,
Mhm,
thanks for the introduction. The like if I turn on, let's say, flux in ADS, like
mhm,
five form flux,
mhm,
that's also an expectation value for a field. That's why we would say that's not a parameter of the theory.
mhm.
But it's not continuous, it's discrete,
Right.
and it takes you between different
Mhm,
central charge conformal
mhm,
filters. It's not a marginal operator.
mhm.
So how does that fall into your studies and classifications?
Um, let's say so. So our argument only applies to continuous family of CFTs, and also I think this conjecture is only true for continuous parameters, because for those discrete parameters there aren't any a corresponding exactly marginal operators, like even in known examples of ADS CFT.
Right, but to say that there's no free parameters in quantum gravity, that would include things like fluxes, I would say, because those
Okay,
are
yeah, that's a good point. So in some sense, what we are trying to prove is a subset of no free parameter conjecture.
continuous ones.
Yeah, continuous one.
And presumably continuous, you mean marginal. That means massless. That means only moduli. Because also you can
Yeah,
have fields with potentials, and it would again take you away from
that's
conformal.
true. Yeah, again take you away from ADS and CFT. Yes.
So you're only claiming statements about continuous moduli, basically, massless
Right. Yeah.
continuous parameters. Okay, thanks.
Okay. So if there are no further questions, let me proceed. So let me so this is a conjecture that we want to prove in the rest of my talk, that I want to prove in the rest of my talk. But let me make a few comments in order to clarify the actual meaning of this conjecture. So the first thing I need to mention is that so this is a CFT conjecture, like a conjecture purely in CFT. But if you consider a conformal field theory without stress tensor, So it's a little bit unusual CFT, but people have discussed in the context of conformal field theory. There are actually many counterexamples to this conjecture. So one famous example is what's called generalized free field CFT. So for those CFT, like we don't really have Lagrangian or anything, but you can just define directly operator algebra. So the idea is that you prepare elementary operator O, and then declare that the 2-point function is given by this power law. But this power law, you can actually the power you can actually arbitrarily tune. So this delta is a free parameter, and if you want to compute more complicated operator involving multiple O's, then you just do the bit construction. So this defines a consistent CFT in the sense you can actually define correlation functions of any point functions which satisfy the crossing equation, and also OP expansion and conformal block expansion. But importantly, this theory does not have stress tensor, because operator O has a random dimension delta, and whereas if you have a stress tensor, the dimension of the stress tensor should be D, which is integer in integer dimensions, and that's not included in this operator algebra. So that's why actually this is a bit considering a theory in ADS without gravity, and in particular, that is indeed true, and you can actually realize this theory in the dual ADS, but just putting some free massive scalar in ADS without gravity, and the mass of the scalar is related to this dimension delta. Okay, and so this is a clearly counterexample, because we can tune the delta arbitrarily, but there is no a marginal operator because O is dimension delta. And so another example, which is also related to the previous example in some way, is to consider a quantum field theory on a fixed ADS without gravity. And if you put quantum field theory on a fixed ADS, then you can still compute some correlation function of operators inserted at the boundary of ADS, and that they satisfy all the nice properties of conformal field theory axioms, like a crossing symmetry, and then operator product expansion and conformal block expansion. But obviously, this setup actually has many parameters, because you can tune the coupling constants in QFT, like a mass of the particle or the coupling strengths arbitrarily. So they basically appear as some kind of free parameters from the dual CFT point of view. So these two examples basically says that in order to really show this statement, it is really important that ADS theory has a gravity or quantum gravity. And the counterpart of that statement is that a CFT really needs to have stress tensor. And as far as I know, this conjecture that I wrote over there, although it was motivated by the semi-classical holographic CFTs, even in arbitrary CFT, as far as I know, there is no counterexample if you consider theory with a stress tensor and discrete spectrum. So there is a famous counterexample, probably many people will bring up in this context, is a Liouville field theory in 2 dimensions. And Liouville field theory has a parameter often denoted by B, which is basically coupling constant of Liouville theory. And however, a change of B is not generated by any exactly marginal operator. And furthermore, even the central charge changes as you change B, this parameter B. So in that sense, this is a counterexample, but and furthermore, it does have a stress tensor. But as many of you know, a Liouville theory has many pathologies. For example, it has a continuous spectrum, and it also has the vacuum state is non-normalizable. So, well, I will come back to this Liouville theory later when we discuss the assumptions that go into our proof. Okay, so let me now go ahead. So the main claim of the paper is that we provided the argument or proof in 2 dimensions, in 2D CFT, under the following 3 assumptions. So the first assumption, so let me first state the assumptions and explain their physical meanings. So the first assumption is the existence of interface. So we assume that for any pair of CFT that are close to each other on the conformal manifold, there exists a conformal interface that becomes trivial when the two CFTs coincide. So we kind of assume that there is an interface which also has a nice property, which is called conformal interface between basically any pair of CFTs on the moduli. And the second assumption is the smoothness assumption, which basically says that the correlation function, which involve a properly normalized operator, properly normalized interface operator, have finite limits as the interface disappears. And the third assumption is a rather technical assumption, which basically says that the CFT, this 2D CFT, has no operators with conformal weights of 1/2 and 1/2 that are neutral under all the global symmetry preserved by the interface. So this third assumption, we are quite unhappy about it, but at the moment, we basically couldn't get rid of it. I'm going to explain why we couldn't. Okay, so this seems a bit complicated and abstract, and also it might sound technical. So let me explain the physical meaning of each of these assumptions.
I have a question.
Yes.
So in the first assumption, what do you mean by CFTs that are close to each other? Do you have like a metric on the conformal manifold by which you define that they're close to each other?
Yeah. So let's assume that you can define a metric on the manifold, and basically our argument is a deal with the infinitesimal deformation. The two points infinitesimally close on the conformal manifold. So any notion of metric that allows you to define the a infinitesimal separated 2 points would work.
Okay, sure, thank you.
Okay, so let's first discuss the first assumption, which is the existence of the interface. So roughly speaking, so for those of you who know for example, the paper by Daniel and Hiroshi about the zero form symmetry, in some sense, this is a bit like a splittability, assuming the splittability of -1 form symmetry. So just to remind you that in their paper, they have argument about absence of zero form symmetry, basically assuming starting from the splittability of charge operators. And so what this basically says is that between the CFT with coupling lambda and a CFT with coupling lambda plus delta lambda, you can find an interface I, which basically separates two regions. So if you introduce an interface, the space would look like this. And what this physically does is basically this existence of interface allow you to kind of locally change. I use the word coupling, but maybe I should have used the parameter. So you can locally change the parameter inside the CFT. And so this assumption, we must admit, it is a rather strong assumption. And it is not and indeed, you might say that it is not too surprising that this assumption is actually closely connected to the existence of the marginal operator, because naively, you can imagine deforming the CFT parameter in a very, very tiny region, and then take a proper limit, and then that might actually allow you to define some kind of non-trivial local operator, because in the end, the region in which the CFT is deformed becomes very tiny. So at the very naive level, you might say assuming this might be almost equivalent to assuming the existence of the marginal operator. And however, this argument is not very rigorous, and if you try to make it rigorous, actually there are many difficulties. And first of all, I said, you can imagine the situation in which you shrink this ball to a very tiny size, take a limit to define some notion of a local operator, but it is not at all clear, and it's actually hard to prove that the limit actually exists. And this left-hand side might just give you 0 or maybe just infinite. And second of all, even if the limit exists, it is not guaranteed that we get this particular exactly marginal operator, which is like a dimension D and then conformal primary. You might just get some other operator, like an identity operator. And in fact, like this happens like if you try to do something similar in conformal field theory without stress tensor, like in generalized free field theory. Like in that case, like this procedure leads to just the identity operator. If you want to like make it fine, if you first of all, like in the case of generalized free field that I talked about, like the defining the limit is subtle, and even if you succeed in getting like defining the finite limit, you oftentimes end up with just getting identity operator. Okay.
Shota, can I
Yeah.
quickly ask?
Yeah.
The splittability of -1 form symmetries is something that follows automatically whenever your quantum field theory has a lattice regulator, for instance.
Mhm.
Is something like that also true for this version of splittability? Like suppose my CFT for any value of the coupling has a lattice regulator. Is it clear that the interface is like this?
Yeah. So, well, okay, I don't have a very intelligent comment. So, like, if the like individual lattice degrees of freedom also carries a parameter, then of course, like obviously, like you can just like change the parameter there. But I don't know like if that's a well
But
that
but
sounds a bit too strong.
but that's then and what the problem is that it's not super
Yeah.
clear, at least to me, that when I make the deformation very small, that's gonna become trivial. There could be like edge effects and
Right, right.
like there could be an order of limits kind
Mhm.
of issue.
Yeah, it's yeah, indeed, like in the case of lattice, like there is a probably additional like order of limits like so this is also like a bit similar order of limits, like when you make it similar, like
Right, right, right.
when you make the region small, then it might just diverge, and then in the lattice probably like introduces additional difficulties. Okay, so this was the first assumption. So let's now talk about
Oh,
smoothness
hi.
assumption. Yes.
Shota, just a quick question. So if I have a continuous family of CFTs,
Mm-hmm.
then what could be the obstruction to making this continuous family vary with space-time to, create some sort of interface? Like what's the possible obstruction to changing this coupling over space-time?
Um, yeah, it depends on like what you are willing to take for granted. Um, but let me just point out that our argument actually uses the uses the fact that this interface is conformal. So even if you accept that, okay, you can like locally change the coupling, the interface between the two might not be conformal.
Okay. Yeah. I mean, intuitively, I would just have said, oh, I vary in one direction and then I do some conformal transformation to make it, conformal
Right,
limit.
right.
But okay, but perhaps there's some.
Yeah, I agree. Like roughly speaking,
Yeah,
that like that's also the reason why like we think that this assumption is harmless, but like to
I see.
really show it, like you need to show that like there's a fixed point in the RG.
I see. Okay. Thanks.
I have a question too.
Yes.
So, so you just said that this interface should be conformal, but since you are deforming it, you also require it to be topological, right?
No, like it's important that it's actually like a conformal, and
Right.
so and also
So
like in the existing examples of ADS-CFT, like this interface is never topological. This kind of interface is never topological. It can only be conformal. And yeah, I guess I can make some
but
comments like later when we discuss, like when I
but as
discuss
far as
the.
I may be wrong, but as far as I understand, if you have a conformal interface,
Uh-huh.
you can satisfy the condition that it requires it to be topological. So as far as I understand,
No,
topological interfaces are like subsets of the
uh,
conformal interface.
uh, sorry, topological interface is a subset of conformal interface, but conformal
Yes,
interface is not a subset of topological
I
interface.
agree. I agree. What you're saying is that these interfaces are conformal but not topological.
Right.
Okay, I see. Thanks.
Okay, thanks for the question. So yeah, okay, so let's talk about the smoothness assumption. So this smoothness assumption that was the second assumption. Like I said, like a correlation function with unit normalized interface operator have finite limits as the interface disappears. So when stated in this way, like it's a little bit, it sounds a little bit technical, but what this just means is that, so let's imagine like you compute some correlation function, like in the presence of interface, and you put some operator here, like in the bulk, or operator here on the left-hand side of the bulk, and in addition, you like insert some operator on the interface. And the idea, this assumption basically says that if you take the limit in which both sides become the same, first of all, interface disappears. But in that limit, like it is not automatically guaranteed that you get some like a finite relation function. You might just get divergence. But the assumption says that you get some finite correlation function, which basically says that this operator O defined on the interface becomes basically like a standard operator in the original CFT, like without interface in the limit. Okay, so this is stated in a technical way, but it basically like we just introduced just to guarantee that interface becomes the usual operator in the limit. Okay. So the third one is the ugliest one, which is the technical assumption, which basically said the CFT has no operator with conformal weights 1/2 1/2 that are neutral under all the global symmetries preserved by the interface. So we impose this assumption because of technical difficulties. Like we couldn't like solve the problem. We couldn't come up with an argument without this technical assumption. And it'll be very nice to remove it, but so far we haven't been able to do that. Another comment is that although this assumption is introduced for a different purpose, like a different technical purpose, but this assumption also excludes the Levy theory from our arguments, because the Levy theory actually has a charge neutral 1/2 1/2 operator. So this assumption automatically excludes the Levy theory. So in the rest of my talk, I'm not talking about the Levy theory. Okay, so far so good.
Sorry.
Yeah.
Quick question. Do you have in mind any examples of interesting CFTs that would have this operator other than Levy, which you already explained?
Let me think. So for example, like a free boson, like a free compact boson, has a radius r, and if you choose a particular radius, there can be this this kind of operator. But at generic radius, I think we don't have any such operators.
Right. Thanks.
And also, like in supersymmetric example, like in 2D supersymmetric conformal field theory, which is known to have a conformal manifold, there are often like a 1/2 1/2 operator, but they are charged under the R symmetry. Okay, so let's now go to the proof. So let me just show again our assumption, like existence of interface, smoothness, and then technical assumption. And in particular, I want to highlight that we are using conformal interface. So in order to prove this statement, we consider the following setup. So we put the basically conformal interface along the real axis of the two-dimensional plane. So, and then on the upper half plane, we put CFT1 with a parameter lambda. And on the lower half plane, we put CFT2 with a parameter lambda plus delta lambda. And we assume that delta lambda is very infinitesimal. And first of all, I was using the word conformal interface, but I was not really explaining what is special about conformal interface. So the conformal interface is special because across the conformal interface, there is a one copy of Virasoro symmetry that is preserved. So if there is no interface, of course, the 2D CFT has two copies of Virasoro, like a left and right. But because of the presence of interface, some of the Virasoro symmetry gets broken. And if you put a random interface, you basically break both Virasoro symmetry, but one copy is preserved. And that is manifested by this often called a gluing condition, which basically states that on the interface, the stress, like this combination of the stress tensor T minus T bar of the CFD1 smoothly goes over to the same combination of the CFD2. So there is a kind of gluing condition. And well, using a simple algebra, you can also rewrite it in this way. T1 minus T2 on the interface is the same as T1 bar minus T2 bar. And in the rest of my argument, in particular, I'm going to focus on this special operator, which is this combination T1 minus T2. But because of this relation, I can also define it as a T1 bar minus T2 bar. And then this operator is called a displacement operator, and it has a special geometrical meaning. Basically, like a small perturbation if you insert a displacement operator on the interface, that is equivalent to like a deforming the interface a little bit locally, like into the perpendicular direction. And using the Ward identity, you can show that the displacement operator has a protected dimension, like the dimension must be 2. And the 2-point function should have this kind of, should have this universal form, which is consistent with the dimension of the displacement operator. And in general, the coefficient, like a normalization of the displacement operator is an interesting interface CFD data, because you cannot, if you define the displacement operator in this way, you cannot rescale it. Like there's a natural normalization of the displacement operator coming from the stress tensor, and then this ND is a non-trivial CFD data. But as you can see from the definition of this displacement operator, D vanishes when two CFDs coincide, right? Because then T1 becomes T2. And because of that, you can immediately say that like in the limit delta lambda goes to 0, this ND goes to 0, okay? And so in that limit, if you're just using D, you just get 0. But in order to extract something interesting in this infinitesimal limit, now we are going to consider normalized displacement operator. We just divide the displacement operator by square root of ND, so that even in the limit, the 2-point function is finite and takes this form. So this is a kind of a trivial manipulation. And so this already sounds nice. This already sounds nice because now, now after taking the limit, the operator this D hat living on the interface should become some operator, local operator of the CFD1 because of our smoothness assumption. And furthermore, we already know that the displacement operator have dimension 2, which is the same as exactly marginal operator. That said, this is actually not enough to really show that this D hat behaves like an exactly marginal operator. For instance, this analysis doesn't tell you anything about the spin of the operator that you get from the limit of the displacement of operator D hat. And furthermore, it is not clear if this is a Virasoro primary or a Virasoro descendant. So now the question you should ask is that, so this operator D hat that you can get by taking the limit, is it a Virasoro primary with dimension 1, 1? So if you can show it, then you can establish that this operator D hat is a marginal operator in CFD1. Okay, because of our smoothness assumption. And now let me tell you the strategy of proving this. So we first analyze some OPE between D hat and T plus T bar in the limit where a CFD1 and a CFD2 coincides. And this you can actually compute using the definition of D hat. I'm going to show the computation. And then you enumerate all the possible operators that satisfy this OPE that you determined. And if you carefully analyze all possible operators, then you conclude that actually there are only two possibilities. Either D hat is a dimension 1, 1 primary, or D hat is a level 1 descendant of dimension 1/2 primary. However, because of the technical assumption that we already assume that the rho is not there in the original CFT. So that's why we conclude that d hat must be phi, which has the same conformal property as the marginal operator. Okay, so that's the strategy. And so now, like, let's, and this is rather like elementary, like this is just like a simple algebraic manipulation. So let me just show how you actually argue for these steps. Okay, so this step one. So we are going to analyze the OP between d hat and t plus t bar. So in order to do that, let's first like consider the original situation before taking the limit, and then consider the OP between t1 plus t2 bar on the and then and the displacement operator on the interface. And I just told you that displacement operator is by definition is given by t1 minus t2. So that this was the definition of displacement operator. So I can rewrite it in this way. And then I just like expand it in this way. So far I'm doing the simple manipulation. So the only non-trivial manipulation I did on the second line is that I used the gluing condition to rewrite t1 plus t2 bar into a t1 bar plus t2. Okay, so, but apart from that, I didn't do anything. And next, we are going to use the fact that the T2 bar and T1 and then T1 bar and T2 actually has no like OP singularities. So this was proven in this paper, and it is actually non-trivial consequence of the cluster decomposition principle. So this one like it takes a little bit of time to explain, so I'm just going to quote the result. So and then if you neglect those terms which do not produce any OP singularities, then you get this combination. Okay. And this combination you can easily compute because this is an OP between the same like a stress tensor of the same CFT. And we know that what's the OP between the stress tensor into the CFT, and that gives you this expression where C1 is the central charge of the CFT1 and C2 is the central charge of the CFT2. Okay. And okay, so this is the expression that you get. And for the unnormalized displacement operator, and if you want to normalize it, you just divide by square root of ND, and we get this expression. Okay. And so far, I haven't taken the limit. So now, in order to take the limit, we need to understand what happens to this combination, because like as I said, if you take the limit, ND goes to 0. So you might worry that this term actually blows up. And in order to understand the fate of this in the limit, we use yet another non-trivial consequence, non-trivial property of CFT, which was derived in this paper, which actually comes from average now energy condition. So again, like this part is a little bit like complicated, and I cannot explain in my talk. But using average energy condition, now energy condition, you can actually show that this ND must be always larger than like a C1 minus C2. So it goes to 0, but it goes to 0 only slower than C1 minus C2.
Sorry, Shota,
Yeah.
can you ask about this? If the two theories are in the same conformal manifold, isn't C1
Yeah.
equals C2?
Yes. In practice, like it's well, in the order known example, and then in fact, like it has to be C1 equals C2. You can actually show it using different arguments.
Right.
But in this argument, the point is that we don't need to assume that.
Right. But it looks like I could just substitute C1 minus C2 equals 0 everywhere, and
Right.
and then couldn't D be 0?
Okay, so let me say the following. So if conformal manifold is generated by marginal deformation, we know that like center charge does not change. But so far, we are only assuming that there is a family of CFT.
No, I understand.
Yeah.
I understand the logic. Yeah.
Yeah, but mhm.
So the central charge related to gravitational anomaly and the argument that that's invariant under small deformations, I think is more general than assuming there's a marginal deformation, right?
Yeah, but here like this is not like a C minus C bar, like a C1 and C2 are like a holomorphic.
Right. Okay,
Yeah.
thanks. Yes. Thanks.
So it's not directly related to gravitational anomaly. Okay, so basically like the whole point of this argument using ANIC is to show that this becomes 0 in the limit. Okay. And using that, you can take the limit, and then in the limit, T1 becomes T1, and then T2 bar becomes T1 bar, and then you get this OP structure. So this basically means that in this combination of Virasoro algebra, actually a D hat now behaves like a primary operator because there is no a higher order poles. And a more appropriate word for this is the D hat is actually interface Virasoro primary. All right, so this shows that the D hat is an interface Virasoro primary, which is a Virasoro primary under the single copy, the combination of the two Virasoro symmetries. So now, if you really want to understand what is this D, then you just enumerate all the possibilities. You start from the representation of two copies of Virasoro and ask which operator can give rise to primary for the single copy of Virasoro. So this is just a representation theory question, and then these are all the possibilities. Either it's a level one descendant of this a conserved current or a anti-holomorphic part of the conserved current, or a level one descendant of this one half operator, or this anti-holomorphic part, or it's a Virasoro primary satisfying H plus H bar equal 2, or it might be stress tensor itself because stress tensor does have a dimension 2. Okay, so and in particular, when we enumerate all the possibility, we are using unitarity because we are not talking about non-unitary representation of the Virasoro symmetries. And then the point is that if you carefully think about it, you can exclude almost all the possibilities. And in particular, the possibility 1 and 2 both feature descendants, right? Rather than primary. And then in general, if you consider descendants, you get a higher order poles in OPE. The OP with T plus T bar doesn't start with 1 over X squared. And using that, you can actually exclude possibility 1, while possibility 2 is allowed only for the particular linear combination of this a partial minus partial bar phi rho. So let me just give you one very quick slide summary of that argument. So so this is a kind of a general structure of the OP between a descendant of the current and anti-holomorphic part of descendant of the current. And as you can see, so this they are the third order pole, and then there's no way to cancel them because they are different operators. And on the other hand, if you consider this guy or this guy, again you have a third order pole, but because the third order pole comes with the same operator, if you take appropriate linear combination, you can eliminate the third order pole. And this basically kills the possibility and possibility 1 and possibility 2. And to analyze the possibilities 3 and 4, we actually need to analyze yet another OP, which is T minus T bar and D hat. But using that, you can actually exclude possibility 4 entirely, while possibility 3 is only allowed for H equal H bar equal 1. So just in case somebody is interested, because of lack of time, let me just skip this. So this basically tells you that only allowed combination is a Virasoro primary with H equal H bar equal 1, or this combination of descendant. So this is the result from the previous slide. And this operator, as I already said, by the smoothness assumption, this must be a local operator in the undeformed CFT1. Because we took the limit in which the interface trivializes. And furthermore, because we assume the technical assumption, there shouldn't be any operator which has the same quantum number as rho. So that basically kills the second piece. And we therefore conclude that D hat in this limit is just given by a Virasoro primary with dimension H and H bar equal 1 and 1, 1. And so extending this kind of analysis, again, using rather a simple property of the displacement operator, you can also show that the 3-point function of D hat vanishes in the limit, which is a famous requirement for exact marginality. And
I have a question.
yes.
Sorry. So when you made that assumption earlier, You said that there should be no operator with h and h bar both equal to 1/2, but you
Yeah.
also said that this operator should be neutral under global symmetry. So why did you assume that?
Yeah. So the correct. Okay. So the assumption is like there is no dimension one half operator that are neutral under the symmetry preserved by the interface. It's stated in a bit complicated way.
Mhm.
And of course, this D operator has the same symmetry property as the interface. So that's why this allows you to exclude this row. But the reason why we wanted to impose that that symmetry condition is that there is a famous example of like a 2D CFT with exactly marginal deformation or like conformal manifold, which is 2D superconformal field theory. And in those cases, like oftentimes there are actually like a dimension one half operator, but they are actually charged. So even for those, they are like charged under the R symmetry. So the point is that like our argument applies to such series, although those series have dimension one half operator.
I see. Okay. Thank you.
Okay. So now let me make some comment. So this basically tells you that like you can extract the exactly marginal operator from the displacement operator. And so now let me just make several comments, especially about the generalization. So the natural question you can ask, so the argument that I presented and also that we presented in the paper is about 2D CFT. So the natural question is whether we can generalize it to higher D. And it is indeed possible. And again, you can extract the marginal operator from the displacement operator. But a representations area of higher dimensional conformal group is more complicated. So there are more possibilities. So we have to carefully study each case. And that's work in progress. And another natural question is can we remove the third assumption, which was this technical assumption? And we very much hope so, but at the moment, it's not that obvious how to remove this technical assumption, unfortunately. So another comment that I want to make is that using the technical assumption, we remove this existence of rho. But you can ask, what is this a weird operator showing up here? It actually has a physical interpretation. So this operator rho, let me remind you that it has a dimension one half operator, which means that the conformal dimension is 1 rather than 2. And it is actually what's called interface marginal operator, which basically generates the one parameter family of interface, not the one parameter family of CFT, but one parameter of interface. And it generates what's called interface conformal manifolds. And the reason why the existence of rho makes the analysis complicated is that in conformal, if you start doing a conformal perturbation theory, and then by deforming this side by operator phi, oftentimes by renormalization, if you go to higher order, the rho also gets generated, and then it becomes very hard to disentangle rho from phi, and that's also what's happening here. The displacement operator is in general a combination, it's a bit difficult to say that phi is non-zero. So even if the displacement d hat is non-zero, it might just come from rho in the limit.
Sorry, Shota.
Yeah.
So to see if I understood, what you mean here is that if there's a non-vanishing rho, that means it's in some sense a one parameter family of conformal interfaces, correct?
Right.
And so then when you run this argument, you can generate an interface or whatever with also insertions of the rho.
Right.
But doesn't that also count? Like if there's a one parameter family, you don't care so much which one you get. So don't these also count as conformal interfaces?
Okay, so this is really a one parameter family of interface itself,
Yeah, I
rather
understand.
than conformal field theory.
Yeah.
But it's okay. It's true. Maybe that's a good point. Maybe we can also try to now reinterpret this from the gravity side, as some kind of parameter
Yeah, there's some
of
back on the brain.
the brain.
Yeah.
Yeah, that's a good point. And And the important, the most pressing or important question that we should ask is, can we derive the existence of interface from something more fundamental? Because as I explained in the beginning, it's a rather strong assumption, because naively you might say that existence of interface almost automatically guarantees existence of the marginal operator, although this is strictly speaking not the case. But ideally, of course, we should be able to derive the existence of interface from something more fundamental. Okay, so these are comments. So let me now go to the conclusion. So the point of the paper was, okay, so in the talk, I basically first explained how to translate the no free parameter conjecture in quantum gravity in ADS to CFT statement, which is basically every conformal manifold must be generated by exactly marginal operators. And we gave an argument for this in 2 dimensions and in 2D CFT, assuming that the interface connecting a pair of CFTs on a conformal manifold exists, and also some extra technical assumptions. And I should emphasize that the key idea was to use the displacement operator. And this idea of using the displacement operator seems powerful also in higher dimensions, which is in work in progress. And as I mentioned, a big open question is whether we can show the existence of the interface from something more fundamental. And let me also just list possible future directions. Of course, one question we should ask is that, okay, so this is one particular example of swampland conjectures. Is there anything we can learn from our analysis, and then maybe use it for proving other conjectures? Of course, let me mention that there have been recent developments about translating a distance conjecture to CFT and then proving them, at least part of them. And so, but the one maybe takeaway or a lesson from our analysis, which might not be which is not often emphasized, is that it seems like thinking of a conformal interface is very useful for achieving such goals. And in fact, there is some ongoing work that I'm discussing with Jose Calderon Infante and Lucia Cordova and Irene Valenzuela, which is about the absence of shift symmetry in ADS, and also there conformal interfaces play an important role. So maybe this is one important lesson. And in particular, if you think about it a little bit, the reason why this is useful is that the conformal interface and looking at a displacement operator, which basically comes from the stress tensor in the bulk, is a kind of a very nice way of taking into account the locality of CFT, or more precisely utilizing the fact that CFT has a stress tensor. I don't have a deep understanding why this is so useful, but it seems like it's useful. And maybe the last comment I would make is that by contrast, if you say that CFT bootstrap, we are more accustomed to looking at some correlation function of local operators. But for the correlation function of local operator, it seems like we do not yet know how to efficiently or effectively derive non-trivial consequence by utilizing the existence of the stress tensor. But maybe by thinking about conformal interfaces, maybe we will understand the deeper meaning of having a stress tensor in CFT, or maybe a better way of utilizing that part. Okay, let me end here.